Hello, everyone. Thank you for being here. I want to talk about lightweight authentication and access control schemes for IoMT systems. I am Seyed Farhad Aghili. I'm an IT engineer. I'm working on information security. My PhD is from University of Isan, and now I'm working on University of Freiburg as a security researcher. And I'm working on energy efficient protocols, security analysis of existing IoT protocols, and authentication and key agreement protocols, which preserve ownership transfer, access control, and secure against compromised entity attack. I work with this Professor Hamid Mala, Mauro Conti, Pedro Peris Lopez, and Christian Schindelhaber. So, a presentation outline. At first, I will introduce Internet of Medical Things, and the first topic is PACIT, which is the proactive authentication and key agreement protocol for Internet of Things. LACO is the next one, which is lightweight three-factor authentication, access control, and ownership transfer scheme for e-health systems in IoT. And the last one is lightweight attribute-based access control scheme for IoT cloud integrated systems using dynamic attributes. So what's IoMT? In the medical systems, we have lots of entities which are connected to the internet and want to transfer the information via the internet. For example, patient has the sensors, implemented sensors, and want to transfer the information to the other entities. So by using this technology, vast majority of patients are based at home and have treated with the telemedicine. We have wireless connection, and the data will store in the cloud, or we have the sensors that collect the information, and we have access to the real-time data by the user with the assistance of the gateway. So we have several standards here. Two main standards here are these standards, but they use lots of cryptographic primitives in their proposed protocols, and they use encryption, one-way comparison, MAC, and so on, which is not suitable for resource constrained sensors, which, for example, use RFID systems that are based on the standard like UPC class 1 generation 2, which has lots of limitations as the gate and amount of the gates and so on. So one of the proposed architecture in IoMT is this, that we have sensor node, cluster head, gateway, and the user, which want to have these three links as they want to communicate with each other to provide the end node to end user connection. So we should preserve authentication, authorization, and ownership transfer for this system. So the first proposal is PACIT, which is presented in Infocom 2019. And what's the problem? The problem is that in this system, we have mobile entities that could be compromised. And what will happen when the mobile entity compromised? We have other attacks such as impersonation attack, secret disclosure attack, DOS attack, and desynchronization attack. Is there any solution in the literatures? No one has succeeded to overcome this attack so far, and lots of them has vulnerabilities. One of them is not lightweight, which use pairing and use the zero knowledge, and some of them needs to hold a complete key after reconstruction. I will explain it after on. So, what are the contributions of the PACIT? It is lightweight, proactive, no need to run the registration phase again for updating the shares. I will explain why we need to update the shares. It can be used for all applications of the IoT like IoMT, and it is secure against entity compromise attack. The idea is using secure secret sharing and discrete logarithm problem. So what is secret sharing? Assume that we have the secret. We use the Tn secret sharing scheme. That T is the number of entity out of n entity that can reconstruct the key. And we deliver these n shares of the secret to the entities, and then T entity out of this entity can reconstruct the secret. Why it is useful for our approach? For example, we have the active attacker who can compromise the entity number 1, cannot reconstruct the secret with only this share. So is there any problem here? Yes, if we assume that we have 2-3 secret sharing scheme, we have 3 entities that want to collaborate together through the time. At the first time, the mobile active adversary compromised V1, which is the share of the first entity. At the time 2, it compromised the second share, and then can reconstruct the secret. Is there any solution? Fortunately, yes. The solution is the proactive secret sharing. In the proactive secret sharing, we can say that, for example, if these 2 entities has these shares that reconstruct this key, update the shares during the time, and then with the new shares, they can reconstruct the same key. We don't need to update the key. With the same key we have different shares. So after the time with these shares, which is the previous and new shares, the adversary cannot reconstruct the key. So our approach is, our proposed protocol is proactive, use this property. Our protocol has the setup and registration phase. In the setup phase, gateway is responsible to run the secret sharing scheme, which is 4-4 scheme. The gateway generates the 4 shares and then keep one of them for himself and stores the share in this form. We use this form to storing the share because of the discrete logarithm problem that I will explain in next slide, why we use this for sharing the secret, and then delivers other shares to the other entities, user, cluster head, and the sensor. So in the setup phase, each user generates the random number and sends it using the hash to the gateway, and the gateway as a response sends them the value of the hash that involves the secrets of the S is the secrets of the gateway, which this parameter F used for the authentication and verification. This is the protocol we propose for this packet, and it has several algorithms and verifications, and also at the end they accept the session key. So I'm not going to the details, but I provide this slide for just speak about the novelty of this scheme. Assume that each entity has the share, and the gateway also has this form of the secret. So the user generates random number and sends his share securely to the gateway. I'm not saying about how it makes it secure and how preserve the integrity and verifications and the gateway side. I just want to say about the novelty of the work. and then the gateway add the share, his share, and sends it to the cluster head. Then the cluster head only sends the random number of the user to the sensor node. Sensor node generates another random number and sends his share to the cluster head. Now cluster head, which has all of the shares, is responsible to reconstruct the secret, updates the shares in this form, for example, but the secret is the same, and also computes the session key and sends the session key a new share to the sensor node. The sensor node also send the acknowledge, and after that it computes G to the power of the secret mod P and the other shares and the secret and the session key and sends it to the gateway. Now gateway can decide that if the reconstructed secret is correct or not. We don't save the exact secret in the database of the gateway because if you can the adversary can access to the gateway memory, it can obtains all the secrets. So after that sends the new share of each gateway sends the new share of the user to the user along with the session key, and at the end we have each entity has the new share and the session key. So in terms of evaluation, we evaluate the security of the proposed protocol informally and formally. In the formal side, we use the proverif language, which is the famous language for verification of the protocols. It is based on the WBO model, and we translate the protocol to the proverif language, and it shows that our proposed protocol is secure. So performance evaluation in the sensor side also shows that our approach, which is the last one, is more efficient than the other predecessor state-of-the-art works. And conclusion for the packet, can the proposed scheme cover the compromised entity challenge? Yes. Is it lightweight enough for using in the IoMT? Yes. Is it proactive authentication and key agreement scheme to satisfy the security against active mobile attacker, compromised entity attack? Yes. Is it a dynamic scheme? Could we increase the threshold of the system, threshold of the secret sharing scheme, or could the number of the nodes change? For example, we add the node or remove the node? No. The answer to this question could be our future work. If in the future we want to focus on design a secure lightweight for the group entities, group of nodes, group of sensors in the patient, which is dynamic, and when we remove or add the entity to the system, or we can increase the threshold when we have the active attacker in which at the same time can compromise more than one entity. The next topic is the access control in Internet of Medical Things. In the access control, we have several entities which each of them can access to part of the information or cannot access to part of other parts of the information. Here we have a discretionary access control model, which is based on the discretion of the data owner, and in the DAC, the data owner, which is the subject, which can have the action to the object, can grant his permission to the other subjects. But in the MAC, or mandatory access control, which is based on multi-level security, access rules are mandated by the admin, not by the owner of the object. So it is the difference between MAC and DAC. So the other access control model is RBAC, or role-based access control. The other name is non-DAC. In this model, users are assigned to the roles. We have users and roles. Then roles assigned to have the access to the resources or objects. So if we want to change the policy, we want to change the access permission of the user, we just have to change the role of the user. We don't need to change the policies. The other one and the last one is ABAC, or attribute-based access control. For example, we have the user role as a doctor, and the context is for example, time in the morning, and action is viewing the profile of the patient. So we have the attributes of the user, role, time, and view, and we can decide that this doctor at this time can access to this information, for example. If we want to if data is stored in the encrypted format in the database, we need to attribute-based encryption, which has two types: cipher policy ABE and key policy ABE, which is presented at the first time in the Eurocrypt 2005. So, classification of the ABE, we have CPABE and CopyABE. What are the difference? In the CPABE, keys are assigned with sets of attributes, and ciphertexts are assigned with access policies, and the situation are different, is reversed for the key policy ABE. Keys are assigned with access policies, and ciphertexts are assigned with sets of attributes. So the work we proposed is the LACO, which preserve access control and ownership transfer for the IoMT system, published in the FGCS 2019, which is the prestigious journal. And the problem here is that we want to preserve the access control, ownership transfer, and authentication for real-time data, which are sensed with the sensor. The other works have authentication without authorization. Here we want to preserve authorization. So what are our contributions? We propose several attacks in the predecessor state-of-the-art works, like traceability attack, desynchronization, and denial of service. We propose lightweight three-factor authentication and access control based on ABAC and ownership transfer. We designed the strings of the dynamic attributes and static attributes along with the ID of the user, and use the hash of this value as the name of the HACO in the protocol. I will explain about this in the next slide. At the registration phase of this protocol, user and sensor register to the medical server and receives the hash of the secrets of the server for the verification. The user also receives the HACO, this signed value, and sensor ID, along with the biometric templates of the user and the flag, which are implemented into the smart card. Which kind of biometric template we used? Based on this classification, we consider to the accuracy and cost. The best thing could be fingerprint, which has not very well accuracy like iris, but it has well accuracy and low cost. It could be suitable for our work. So what's how protocol works? At first, user log into the system with the biometric template and password and ID, and also sets the flag to 1. We use flag for overcoming to the traceability and impersonation attack. Sends the random number of the user, sensor ID, and HACO to the cluster head or gateway. Cluster head decides on HACO and check the access policies. If the user can access to the information, sends the request to the sensor node along with the random number of the user. The sensor node computes the session key with the new random number of the sensor node in color yellow, and then sends the session key to the cluster head. Now cluster head sends this session key to the user, which have the permission of the access to the information, and the user now can get the real time information of the sensor. Then set the flag, reset the flag to the 0. In terms of security, we also evaluate the security of the protocol using ProVerif here, and performance in the sensor side shows that the result shows that our approach is really lightweight and can use implemented to the real world. Conclusion for LACO: can the proposed scheme provide the 3-factor authentication and access control? Yes. Is it lightweight enough and proactive for being employed in IoMT system? Again, yes. And does it provide a secure ownership transfer? Yes. Why it can do it? If it has another protocol, I cannot explain it at this time. If two users send a request to the medical server, the medical server can transfer the HACO string from one server to the other server, and then to the other user, and then the next user can access to the permission. We should preserve 3 important things here. The old owner of the information it should not be access to the information so far after this ownership transfer, and the new user should not access to the past transaction that happened in the past, and we should not find the fraction of the time that the 2 users can access to the information at the same time. It can preserve these properties. Does the scheme define the policies for access to the stored encrypted data? No, because we don't store the information encrypted into the cloud or into the medical server. The answer to this question is the next topic: lightweight attribute-based access control scheme for IoT cloud integrated systems using dynamic attributes. It means ABAC. We consider to the dynamic attributes such as time, location, and static attributes such as role. Access control is based on key policy ABE, and we have revocation of access permission, which is important. In this architecture, the sensors of the patients transfer the information to the secure, encrypted the information and transfer it to the cloud, and the user use the key which is delivered, which received from the attribute authority, and then decrypt the information which downloaded. The architecture here has the attribute authority, which delivers the attributes for encryption to the data owner, and sends the encryption key along with the policies to the receiver, and then the data owner upload the information to the cloud, the encrypted information, and the receiver can use the received key and use the sensors for which implemented in the device, the sensors for extracting the dynamic attributes, and then can compute some necessary information to decrypt the data. So how protocol works in attribute authority, we run the setup algorithm, which as input we have the random number. It is the elliptic curve. At the output we have public parameters with the master key. Then the master key and the set of the attributes, I mean gamma, are the input of the key generation algorithm, and the output is the decryption key which we send, the attribute authority sends to the user. Then send the public parameters and two kinds of the attributes. With the first one is the static attributes, and the second one, the sigma, is the dynamic attributes to the data owner, and decryption key along with the public parameters to the user. Then the data owner runs the protocol, runs this algorithm, which as input we have the message, set of attributes, and public parameters, runs this algorithm, and at the output we have the ciphertext. In the user side, the user uses the decryption key, public parameters, and the uploaded ciphertext, and then runs the algorithm, and as output we have the message. I don't want to explain about the details of these algorithms, but the important thing here is that again we have dynamic attributes, hash of dynamic attributes here, and we use it for encryption and also for MAC. And in the other side, in the user, we have the same dynamic attributes sensed by the sensors implemented to the device of the user. We use hash of them, and we concat it with the key, which is the output of the access tree of the user, and then use it for the decryption and verification of the message, for the integrity of the message. Transmission cost of the AD scheme, as you can see, compared with the other works, is related to the number of the attributes and the size of the message that's uploaded to the cloud or to the medical server. In our work, we have the size of the message is more or less than the others. And here, which is important, communication cost can be reduced by considering the dynamic attributes. For example, the system's policy is that we should have 10 number of dynamic attributes, 10 number of attributes. Assume that we have 1 dynamic attribute and 9 static attributes. The message size is this. So if the number of attributes is constant, but we increase the number of dynamic attributes and decrease number of static attributes, the size of the message can be decreased. So by increasing the dynamic attributes, we have same number of attributes, but the the size of the message decreased. So, as conclusion, can the proposed scheme provide the lightweight attribute-based access control? Yes. Is it based on the dynamic and static attributes? Yes, which is important for the system. Does it provide a revocation of access permission? Yes, but why? We have the device delivered to the user, which is based on the static attributes and dynamic attributes. Dynamic attributes are obtained from the environment. We cannot change it. If the user is the same, will be in the same time and same place, but we can change the static attributes by programming again the user's device. Does the scheme robust against all forms of computing attacks such as quantum computing? No, the answer to this question could be the future work. For example, we can use post-quantum cryptography like lattice, which is lightweight, can use here, and post-quantum for the next work. These are the references that I used for this seminar, and thank you.